Good. Agenda is Bayesian networks. What are they? Let's see some examples. Suppose you are trying to determine if a patient has COVID-19. You observe the following symptoms. The patient has cough, has fever, and patient has difficulty in breathing. Right? What do you do? Right? We are not 100% certain that the patient has COVID-19 because of the symptoms. Right? We are dealing with uncertainty. Are there models dealing with uncertainty? Are there models where we can model uncertainty? There are many. Right, one among that is what you call the probabilistic way of looking at things. Right. So now suppose you are an X-ray and observe that the patient has a lung infection. You believe that the patient is infected with COVID-19 is now much higher. You have more of an evidence, right? So evidence will strengthen your belief. That's what the Bayesian inference is all about, right? So basically, in the previous slides, what you observed affected your belief that the patient is infected with COVID-19 because you have seen a lot of things like what we call patient has cough, patient has fever, the patient has difficulty in breathing, and now you have an X-ray to strengthen your belief, right? So your belief is strengthened. So this is called reasoning with uncertainty, and this is you can actually leverage the theoretical science of Bayesian reasoning to model this context and say like, okay, yeah, my evidence have more evidence to strengthen my belief, and I've shown you a similar context when you add more and more features with what you call stronger evidences, your what you call your belief on hypothesis or class labels keep changing. We have seen a very similar context in the case of when we were looking at naive-Bayes classifier. Wouldn't it be nice if you had some methodology for reasoning with uncertainty, and we have that's Bayesian reasoning, right? And Bayesian network is essentially a graphical representation of this context. We want to represent and reason systems that is based on conditional independence, right? So if we can presume conditional independence, how do we go for a compact representation of conditional dependence or independence, and then how do you reason about it? And they got what do you call named after Thomas Bayes, coined by Judah Pell in 1936 too. That's what her what do you call the person's what do you call the lifespan is. So this is basically it's called the Bayesian network. It's essentially a graphical model. A Bayesian network specifies a joint distribution in a structured form. So it's a graphical model representing conditional independence. Represent independence or dependence via a directed graph. We're going to see examples. So the nodes will represent the random variables that you see, and edges will represent the independence, the primarily the direct dependence, right? Edges will represent the direct dependence, and nodes will represent the random variables. Is what a Bayesian network is essentially all about. The structure of the network of the graph will depend on the conditional independence relationships, right? So because the graph is acyclic, that's assumption. Two components: the graph structure and the numerical probability. That's what it makes. So a Bayesian network is composed of nodes and edges. Nodes are essentially the random variables, and edges will be their dependence, right? The dependence will be represented over the edges, and the graph structure, right, is essentially like represented by the nodes and edges, and there will be probability values associated over the edges. So essentially, over the relationship, basically the numerical probabilities. Which is essentially like which is essentially you can visualize it across the edges. Basically, each variable given its parents, how are they connected? Are they dependent? Are they independent? Or what is the kind of relationship that you have between these random variables? That's what is represented in terms of numerical probabilities. These are called the probability tables. You get conditional probability tables, right? We're going to see it. So a Bayesian network will look something like this. In our case, so basically you have got random variables: has cough, has fever, has difficulty breathing, has lung infection, and there's another random variable called has COVID. So this is the way in which what do you call in which a Bayesian network will the structure of the network will typically look like, and they find applications. And these are just a few applications. They are extensively applied in various application domains. And so this is an example for a Bayesian network. A Bayesian network is made up of, I told you, a graph, a directed acyclic graph in this case, and a set of tables, a probability tables, right? In this case, you can see that you can say that the variable. So there are four random variables here: A, B, C, and D, and there is a relationship, right? Basically, B can affect C, and so you can if you look at the probability tables, A is basically you can think this as So A can be, let's assume that these are Boolean variables. So A can be false or true. A can be false or true. We'll see more concrete examples a little later. A can be false or true, and probability of A being true is false is 0.6, and probability of A being true is 0.4. So you can think of these as sort of prior, right? So, and all these are Boolean variables. So which means that so given what you call, I mean, see, you want to find the relationship between A and B. Basically, so given A is false and B is false, right? What's the probability of? I mean, you want to given A is false. What's the probability of what you call B being false, right? That's basically you want to so conditioned over A. How do you represent the conditional dependence of B over A? Right, that's what is represented in this probability tables. Basically, dependence of is a conditional probability of B given A, right? That's represented in the conditional probability table, which is essentially capturing the relationship over here. That's what I said, the relationship over the edges. All right, conditioned on A. So if B is false, what is probability of A being false? And what's the probability of, if B is true, what's the probability of A being false? And likewise, right? You get, so these are Boolean variables, which means that you get 2 raised to 4 combinations, and you get the probability assignment for all the 4 combinations. So it's true with, and we can now see, like, what do you call, a given B, how what do you call, what is the probability of C, right? Probability of C given B and probability of D given B. So this is given all these probability tables, right? Conditional probability tables. So given B and D, I mean, these are all Boolean variables. You get 4 combinations, and of given B is false, for the probability of D being false, and probability of what do you call, uh, B given B is false, or the probability of D being true. So basically, you get that conditional probability assignment. So this entire stuff makes what is called a Bayesian network. So Bayesian network is essentially a representation of the conditional dependence between the random variables and the corresponding what do you call conditional probabilities, represent as probability tables. So it's essentially it's a representation. It's a convenient representation, a compact representation of a conditional what do you call dependence or independence context in a problem, right? That's what it is. It's actually a mathematical tool through which you can represent the conditional dependence between a set of random variables, or independence between a set of random variables and the corresponding values. So that compact representation is called a Bayesian network. If you can construct something of this kind, you can reason with it. That's the beauty of this network. So it's a direct acyclic graph. The same explanation. Each node in the graph is a random variable. A node X is a parent of another Y. If a node X is a parent of another node Y, right? If there is an arrow from node X to node Y, and A is parent of B, A is the parent of B, A is the parent of B. So basically, like, see, B is dependent on A. That's what it is. Informally, an arrow from node X to node Y means that X has a direct influence on Y. So which means that B has a direct influence on C. That's what it is. I've already mentioned this. Then you have a set of tables. So set of tables are essentially the conditional dependence tables. I mean, basically, like, I mean, it essentially shows like the conditional probabilities, conditional probability distributions. That's what it is, right? That's what it's called, the conditional probability tables, or CPTs, conditional probability tables, or CPTs. So in essence, what is a Bayesian network? Bayesian network is a mathematical tool. It's a mathematical tool with which you can graphically represent the conditional dependence between a collection of random variables and the corresponding conditional probability values. That's what it is. That's what is called a Bayesian network, right? If you can represent your problem as a Bayesian network, you can reason with it. And constructing a Bayesian network is another interesting aspect. I'll give you pointers there, but it's a little difficult, but I'll give you pointers there. So conditional probability distribution given, so I've already told you, given a combination of values, you can, how do you collection of random variables, how do you represent the conditional dependence between, right? And we have already explained this part. All right. So that's good. Bayesian network, 2 important properties: encode the conditional independence relationship between the variables in a graphical structure. That's the most beautiful part of it. And it has a compact representation of the joint probability distribution over the variables. Let's see, like, what is the meaning of second statement. All right. If you want to compute joint probability, say for example, if you want to compute probability of A, B, C, D, etc., given whatever, right? Given some condition E. condition of a variable E, then how do you compute? If there are, is there a conditional dependence between what you call E and A, B, C, and D? If that's the case, what is the relationship? If E is connected, so can we assume some sort of a relationship between these variables, and then can you bring down the extent of primarily? Can you simplify the computation? That's the kind of question that you're going to see. Right? We'll see examples there. So conditional independence, the Markov condition, that's essentially, this is an interesting aspect. Given its parents, P1, P2. So let's look at this diagram. Given the parents P1 and P2, right, a node X is conditionally independent of its non-descendants. Is conditionally independent of its non-descendants, ND1 and ND2. This is what the Markovian assumptions. So this is why, like, kind of given basically the parents P1, so X, you can say that X is conditionally independent of its non-descendants, right? So joint probability distribution due to Markovian condition, we can compute. This is an interesting aspect. So which says that you don't have to write. I mean, given its parents, you can say that, hey, your what do you call your joint distribution can be your joint probability distribution. The joint distribution that you're probability distribution that you're considering can be computed in easily fashion, right? Due to Markovian condition, you can compute the joint probability distribution over all the variables x1 to xn. You want to compute x1 is equal to x1, etc. So basically, you want to compute this, and you know that see, xi is only dependent. Xi, the random variable xi, is only dependent on its parents. Right, you don't have to worry about anybody else. That's essentially the Markovian assumption. Right, that's what it gives. That's the beauty of this. So which says that you can actually compute, you can actually take a product. So otherwise you have to, so how do you do this? And we're going to see that in a later detail. So pi of xi given x into given parents of xi, that'll be like kind of, if you multiply those together, you'll get the joint distribution, because you don't have to worry about the other variables. That's what it is. Where parents xi means the value of the values of parents of the node xi with respect to the graph. That's what it is. You have to worry only about, like, given condition. I mean, this is dependent only on its parents. That's what it is. You don't have to worry about anybody else. You multiply them together and you can get the joint probability. Right? That's the beauty of the conditional independence assumption. Using the network in the example, suppose you want to calculate, right? That's an example. Probability of A is equal to true, B is equal to true, C is equal to true, and D is equal to true. It's a joint distribution, right? How do you do it? Probability of A is equal to true, right? Probability of A is equal to true because A is not dependent on anybody else. Probability of what is see, this can be right. I mean, see, B is only dependent on A. So probability of, we can written as probability of B is equal to true given A is equal to true. All right, and right, that's the second part. And so you need to get this, right? So probability of C is equal to true. C is equal to true. C is dependent only on B. So you can say, like, yeah, C is equal to true given B is equal to true, right? B is equal to true. That's a condition that your condition. So, and the last one is probability of D. D is dependent only on B. So probability of D is equal to true given B is equal to true. Right, you can just multiply. Otherwise, how do you write this? You have to write probability of A given whatever, and then probability of A given B into probability of AB given. So I mean, we're going to see that you get a very complicated equation, which gets simplified only because you have a proper definition of your dependence relationship. Right, using the network in the example, suppose you want to calculate. That's what it is, and that's what it is. Let's look at this joint probability. What is happening over here is what's called the joint probability factorization. Let us, and those who are done math from your math for machine learning, this will be pretty straightforward. For any joint distribution of random variables, the following factorization are always true. So this is what I want to say. Probability of A, B, C, D. Joint distribution of A, B, C, D can be written as probability of A into probability of B given A into probability of C given AB into probability of D given ABC, right? This is what the factorization formula is. But the moment you know that D is dependent only on C, this will get simplified. You can say, like, C may be dependent only on B. So which means that probability of ABC in our case is probability of BCD basically, like, kind of into. So this is another, what you call, we derive repeatedly by applying the Bayes rule. What is this? So this can be, like, this can be proven. So that's a proof over here, which you can actually, like, kind of, how do you prove this? All right. So but this becomes, like, this is basically, see, this is true for any joint distribution, and this is proven here. ABC basically, what you do is, yeah, it's it can be written as BCD given A, BCD given A into probability of A. This is, what is that? This is a definition of conditional distribution, conditional probability, right? So this can be again split further, and then you can say like CD given B A into B given A into etc etc. You can actually derive this. So that's a derivation there if you want to, if you're interested. But most interesting part, this is a generic factorization. But given your context, A B C D P A B E given A C given A B into P D given A B C, right? This is what you need to do, right? But in our case, what you can do is, probability of A P given A is fine, but C given AB, right? C given AB, you don't have to, right? Given B, I don't have to worry about A, right? C is conditionally independent of A, provided its parents, right? B. So C given AB can be written as probability of C given B, and probability of D given ABC can be written as probability of D given B. So this is the beauty of what do you call having an explicit representation of the conditional dependence. The moment you have this conditional dependence assumption being put out there, your computation will become straightforward, right? That's what it is. So that's why you bring in such a mathematical tool, which can beautifully represent the conditional dependence relationship between random variables, and the values being represented using as a graph, and the values being represented as a collection of CPTs, right? Conditional probability tables, right? So how do you use this Bayesian network? You can use it for inference using Bayesian network to compute the probabilities. Is called, the required probabilities is called inference. So this is what we have done one inference here, right? We wanted to compute the probability of A, B, C, D all happening. We have computed the probability, right? This is an example for inference. In general, inference involves queries of the form, right? Compute the probability of X given E, right? Given an evidence variable, how do you compute the probability of a query variable, right? X, that's what it is. Let's see examples, right? So for example, you want to compute the probability of COVID-19 is true. So the person has fever and a cough. So you can compute. That's an example for what you call inference. Let's see a solid example, a little more solid example, right? It's an example. So this some of these examples I've taken. Most of the examples I've taken from the web, so that you get that notion of inference, right? Right. So I'm at work. Just understand this context. I'm at work. My neighbor John calls to say that my alarm is ringing, but my neighbor Mary doesn't call. Right? Another neighbor called Mary doesn't call. Sometimes it's set off. The alarm is set off by a major earthquake. A minor earthquake, or it can even be by a burglar. Right? There can be a burglary attempt, and that can be one of the reasons. All right. If this is the case, what are the variables that I need to call? So there is possibility of burglary. There is an earthquake possibility, and the alarm is ringing. So and all these are Boolean variables. John calls and Mary calls can be true or false. So I've got 5 random variables here, right? And there is something called a network topology. So there is a causal relationship, which means that the alarm can be set off, can ring either due to what you call a minor earthquake or a burglary. And if there is an alarm, Mary or John can call, right? A burglar can set up the alarm, an earthquake can set up the alarm, an alarm can cause Mary to call, and an alarm can cause John to call, which means that there are conditional dependence relationship between the variables under consideration. All these are Boolean variables in our case, right? So you represent this in the form of a Bayesian graph, right? Bayesian network, and it looks like this. So John alarm, when an alarm, right? Alarm can cause John to call, Mary to call, and alarm can be either due to a burglary or an earthquake, right? So we have got priors, or I would call the what do you call the marginal probability values of B and E, basically an earthquake and a burglary. That's there. So it can be the probability of burglary being true and earthquake being true. You have probability values out there, and conditioned on the burglary or earthquake, you get the CPTs primarily. Like, okay, so if there is burglary being true, probability of, you can actually, if you don't want to represent like this, you can actually represent it in terms of what you call 2 tables. That's also possible. So in our case, we are representing the probability of an alarm, right? A true value for an alarm, true, burglary true, alarm true 0.95. Then you can have burglary true, alarm false will be 1 minus 0.95. And like this, you can, if you want to split it, this is basically a little more compact representation. So burglary and earthquake, probability of alarm being true is 0.95. Likewise, you have represent the other so there are two variables here. So you get four combinations, and for the four combinations you get what you call the probability value, the CPT tables. If you want to split this CPT table into like two parts, that's also fine, but typically this is how it is being represented, right? And then there is basically what you call there is another CPT which represents, what is this representing? This is representing the probability of John calling, what do you call John calling, that's probability of John call being true, right? True when alarm is true or alarm is false. So like if you want a four thing, a what do you call four row thing, you can also make that, which is basically the false aspect also, which is easily computable from here, right? You can actually what do you call, you can say alarm and John, true false, false true, and false you can do. So this is more of a little more compact representation. Again, you can, so four things are actually represented over here using two rows, right? Mary calls, probability of Mary calls given alarm true is what is given here, right? Alarm true is here, and Mary false, Mary calls when alarm is false, that's also given here. So what do you do with this? How do you infer this, right? How do you infer with this? I want to compute, I told you, right, with the Markovian assumption, you can say like the joint distribution can be represented as the product of what you call the probability of xi given its parents, right? In our case, probability, if we want to compute, the question is this: probability of John and Mary calls and alarm rings and no burglary and no earthquake, right? We want to compute the probability of, we want to infer the probability of, there's a call from John, then there's a call from Mary, and there is an alarm, but there is no burglary or there is no earthquake. How do you do that? Probability of John given, so you know that John, so you want to compute, John is already, basically John calls is already dependent on alarm, Mary's calls is also dependent only on alarm, and burglary is basically like, I mean, alarm is already dependent on either burglary or earthquake, and then you can actually, you have the corresponding probabilities, right? So how do you bring in, right? John is dependent only on the alarm, and Mary's call is only dependent on alarm. And what is the probability of what you call an alarm where these two are, this is dependent only on the burglary and earthquake. So not what you call burglary or no earthquake, you can actually you can compute that. And then what you need to do is, you know that B and E are basically not depend on anybody else, so you can actually look at not B and not E, this part of the thing which is not dependent on anybody else. So you just get the values there. J given A is 0.9, right? Mary given A is 0.7 into, so basically A given not A not E, right? Not A not E is basically 0.001. How do you get this? Not A not, what do you call, it's both are false, it's right. Alarm is 0.001, not both are false, alarm is 0.001. All right, you get that value, and then there is what you call the probability of not B. What is probability of not B? So probability of B is this, not B is here, all right, and probability of no earthquake, all right. So you get 1 minus that, right? 1 minus 0.001 is 0.999 and 0.998. You multiply that and you get, right? So your computation, your inference was pretty straightforward because you had the conditional dependence. So you use this. So given its parents, the probability can be like kind of computed, and the conditional probability can be computed, and that can be multiplied together to form the joint probability, right? Another inference example, in our case, suppose we know that A is true. What is the what is more probable, C true or D true? For this we need to compute, right? Probability of C given A is equal to true, you need to compute this. You can actually like kind of, you need to compute. So this can be computed as C true, A true given A given true. So this can be computed. This is basically a probability of AC. How do you compute probability of AC? You can compute like this, right? So from this you can actually like kind of compute, you can actually answer this question. You can infer what is the probability that C is true, right, when or D is true when A is true, right? So you want to compute the probability of, we know that A is true, what is the probability that C is true or D is true? So such an inference, such a question can be easily computed from here. All right. So likewise you can actually like kind of extend this computation to any extent. You can actually have a lot of computations over here. I don't want to spend a lot. And this is basically like kind of, all you assume is that the moment you have the what do you call the dependence on the parents, and the parents are defined over the graph, you can actually independently multiply them together and then compute the corresponding probability values. Right, you can compute all sort of steps there. So baseline, right? There are multiple kinds of inferences that people ask on a Bayesian context. A Bayesian graph can be a diagnostic inference from effect to causes. So, for example, this computation can be like, what is the probability for burglary given John calls? Right, it can be causal inference, right? A burglary causal inference, like if whether John has called based on a burglary, you want to compute that probability. That's called the causal. Does that, I mean, can we compute the probability of a cause, right? Can you infer, right? And can be intercausal, meaning like causes of common effects. Say, for example, say burglary basically happens because basically there's an alarm and there's a burglary, basically. Like, and intercausal is another example. Is alarm and earthquake happened and there was a burglary. Basically, sort of it's a mix of both. So all sorts of questions can be asked there. And so this is all interesting. Even a Bayesian graph, we can easily use this particular aspect, the Markovian assumption, and then you can compute joint probabilities and infer from the Bayesian graph. This is very interesting. But the bad what do you call part is this is easy for a small graph, but for a large network, this takes a long time, and people are researching a lot on approximate inference mechanisms on Bayesian networks. This is another interesting research area that people maybe that some of you can pursue if you want to. Right? Bayesian inference over pretty large Bayesian networks is an interesting problem to pursue. Right? So that's all fine. Given a Bayesian network, which is essentially representing a collection of random variables and their relationships, the dependence relationships, and the corresponding conditional probability values, you can essentially use that Markovian assumption and then compute joint probabilities and answer questions. And then you can essentially do inference on top of it. That's all good, provided you have a graph. How do you construct a graph, right? This is not what you call. It's not very straightforward. We still haven't had said how do you get there. Right? There are two approaches. Some expert design can give to you, right? Other is learn it from data. Right, learn it from data. Let's look at that example that we have seen earlier. How do you construct a graph? I've got a problem statement. I've got a problem context. I'm at work. Neighbor John, who generally ring me up to inform an unusual event at my residence, reached me to say that my alarm is ringing. But another neighbor, Mary, who occasionally called on an alarm, doesn't reach me this time. The alarm is occasionally set off by minor earthquakes or otherwise by a burglary attempt. I have enough of experiences, right, of Mary calling, of John calling, earthquakes happening, burglary happening, and what you call context where Mary call when there is an alarm, Mary doesn't call, John calls, John doesn't call, alarm is set off because there is set off at, or alarm is ringing on situations where there is earthquake, there is no earthquake, there is no earthquake and no burglary, right? So I have data on all these possible combinations, and how do you build such a network? Can we construct a Bayesian network to capture the above context? This is my problem context. I've got enough of data, experience, right? So that my statements can be quantified. Sometimes can be quantified. I say like, yeah, I know like 20% of the time alarm can be set off without an earthquake. So I've got enough of data to compute. How do you compute? With the likelihood ratios, right? You know that, you know how to compute likelihood ratios, right? I've coined a coin 50,000 times, and now I have a means to compute the probability of I can do a probability assignment over my experiments, and I can say like, oh yeah, looks like a fair coin, right? Probability heard is near to 0.5, whatever, right? So I have such data. Can you construct a Bayesian network to capture the above context and possibly reason with it? How do you go about doing this? What's the first step? The first step in constructing a Bayesian network is we need to identify the random variables, right? Burglary, earthquake, alarm, John calls, Mary calls. These are all the random variables. We identify those random variables, and then we identify the topology. How these things are connected, right? We can say like burglar can set off the alarm, earthquake can set off the alarm. So basically, we need to identify the causal relationship between the variables, the causal relationship between the variables, which is essentially the dependence relationship between the variables. Once you have the dependence relationship between the variables, what do? You represent it. You order the variables in terms of the causality. You say like, okay, alarm. Earthquake or burglary can cause the alarm, and alarm can cause John and Mary to call. That's what it is. That's how my causal relationship is, right? Once I know this, the conditional dependence, these assumptions are reflected in the graph structure. You can represent in terms of a graph. You get a graph with 5 nodes, right? I get a graph with 5 nodes. So I have got A at the end, the middle, E and B affects A, A is affecting J and M, right? That's what the graph is, right? Once I have that, I need to compute the probability tables, compute the marginal and the conditional probability tables using the expert knowledge, or you can ask somebody to give me the numbers or the assignment, probability assignment, or can compute it from data. All right. So for example, PEMAJ, whatever, right? I need to compute the joint probability. You can see one way is like once we know like these are the random variables. One way is like you explicitly list down all the combinations, right? Join probability values, and then do this, get assignment for everybody, which is, you may not have enough of data to give all the combinations. What you do is you essentially, like, you don't have to do that, because now you have a conditional dependence assumption, conditional independence assumption, right? So we can either it's 2 raised to 5 32 probabilities, and you don't need all these 32 probabilities, because once you have this kind of a causal relationship being identified, you don't need values for all these stuff, right? You need only values, because you know that the what you call the certain things are dependent on certain other random variables, are dependent on certain other random variables, right? That relationship is available there. So what you do is you initially find this graph, right? I need to know that now I need to represent 2 marginal probability values, and so which means that I need to compute 2 marginal probability values, basically the tables, and correspondingly, like, I've got 3 conditional dependency tables, right? CPTs, conditional probability tables, and I need to, what do you call, put these values based on the data available, right? Data, where do you get data from? Either if you have data, you compute it, right? Basically a likelihood ratio you can compute. Otherwise, you can ask somebody to assign it. And once you have that, what you do is you draw the network with the CPTs, and that becomes your Bayesian network. And that's pretty much about Bayesian network. It's an interesting mathematical tool to represent conditional dependence between what do you call, variables, and random variables, and the corresponding what do you call, probability assignments being represented as probability tables, and you can reason with it. And if you are given a context with enough of data or expert knowledge, you can build it, infer with it, and that makes your life of inference easier. So this is an interesting mathematical paradigm, and I want to stop here, and we can possibly take some questions later.